So first of all, I would like to thank the organizer to make this possible, this wonderful workshop in Warsaw. And I'm Xin-Yu Luo from Max-Planck-Institute for Quantum Optics. And today I'm presenting our program on recent results to create a big molecule from degenerate Fermi gas for microshielded Fermi-Hubbard dynamics. So essentially, in the last few like 10 years, we are struggling to understand and control the in-mass collisions between the ultracold molecules. And it was a pain, but if you manage to control them, you can do wonderful things which we cannot imagine even two years before. So I think Sebastian has given a wonderful introduction to the field of ultracold molecules. I just briefly repeat this from my viewpoint. And first of all, the dipolar molecules excited very strong and tunable anisotropic dipolar interaction, which can give rise exotic quantum nanobody phenomenon. And this field essentially started like 15 years ago by the pioneering work from David and Junior's group. And the molecules exhibit really rich internal degree spreading, ranging from like electronics, liberation and evaporation to translation degree freedom. And those many degree freedom are both blessings and curses. They give rise to really broad applications, including cold collisions and chemistry, and quantum simulation, and quantum information processing, and to like precision measurement, like EVM and so on. But this also makes cooling molecules extremely difficult because the traditional laser cooling method doesn't apply to molecules directly. Also, the collisions between molecules are complicated and intrinsically unstable because the many states involved. So up to now, there are two main methods to create ultracold molecules. Direct cooling, especially laser cooling, progressed really fast in the recent years and can already reach 1 microcarats, a few species. But another way of like taking advantage of the developed cooling technique of atoms, which assemble atoms into ultracold molecules, can reach even lower temperature, 20 nanokelvin. So today I'm going to talk about how we solve those long-standing issues like the unstable collisions and how we make quantum degenerate gas of NK molecules and find a new type of scattering resonance, and with which we can combine the dimers into a tetramer. So this field is still booming even after 15 years. Like, it's really amazing. So here I just pick up a few examples, like recent years, like how the field gave interesting results, such as EDF measurement down to 10⁻30 precision, and recently, like in Harvard and so on, they observed the ultracold chemical reaction directly. And in GILA and our team and US team, we create the degenerate Fermi gas of NK molecules. And last year, we observed a new type of scattering resonance, like field link resonance, like tetratomic molecule. And very exciting, in Princeton and Harvard, people have controlled molecules down to the single molecule level. Yes. So in our lab, we are most interested to study ultracold dipolar nanobody system. So here, just give you an example. Like on the left side is an extreme of magnetic atoms, which exhibit relatively weak dipoles, but collisional stable. So people can prepare those magnetic atoms into really deep quantum degeneracy and already studied latent and to super solid, which is really beautiful. On the right side is the Rydberg atoms, which features very strong dipoles, but relatively short lifetime. People can show a very beautiful result, with fixed dipole rings, like starting DC models and exotic spin models. Molecules is something in between, which features a field by medial dipoles, and they are stable when they are alone. So in Jun's group and the Princeton group, other group has studied this spin model dynamics in fixed molecules in lattice. But what if we can control the collision loss? So there are multiple exciting possibilities, including like pivot superfluid to like phonon modes in lattice. So thanks to the recent breakthrough in this quantum degenerate gas in a few labs, those and just show you a few examples how those new possibilities looks like. For example, as I will show later, when the dipole interaction is strong enough, those molecules can form a weakly bound state, which is called fielding bound state, and give rise to a new type of scattering resonance. And this can give you a dipolar PCS DC crossover. And below a certain critical temperature, one could observe this pivot superfluid with this anisotropic barrier and form a DC atomic molecule. For bosonic gas, it's possible, like as Kim and his colleagues predicted, one can observe from droplets to crystal and so on. So, but we need to first solve those problems. Like we need to stabilize those molecules, and we can do those things. So this is my topic of my talk. I will first talk about the mystery of the collisional stability of molecules, and show you how we stabilize molecules with macro shielding. Then the observation of fielding resonance, and with which we form this bigger molecule. So, like 15 years ago, when the Gila team created PRB molecules, they immediately noticed PRB molecules not stable because of these chemical reactions. So CRS has predicted that AK molecules in theory are chemically stable against two-body collisions. But it's turned out for almost all the backing molecules, they exhibit near universal two-body loss. So this is an example that our measurement on AK molecules loss. Like the measured loss rate agree pretty well with this universal loss limit set by the temperature divided by the centrifugal barrier height. So when we turn on the electric field, this loss becomes even worse because this head-to-tail attractive collisions reduce the barrier, centrifugal barrier. So this is a really big problem because the good to bad collision ratio is too low for efficient rapid cooling. So why did those molecules exhibit those huge losses? There was a hypothesis, the so-called sticky collision, because those molecules, when they couple to very short range, there are many states involved, so they have to go through all of these configurations with near close energies, and they stay together before they find a way out. So the spinning time is predicted to be proportional to this sensitive state divided by the channel of this K. So just like 4 years ago, Christine Arthur proposed that those long-lived collisional complexes could be excited by photons to excited state, then decay to other channels. So this was soon confirmed in experiment, for example, in Simon's group and in Campus group, and the measurement of the speaking time and the photoexcited rate really agree with theory. This gave us the hope that we can save sodium potassium molecules in dark trap. So we spent quite a long time to prepare this dark box trap to save NAK molecules, but it turns out the two-body loss rate is almost independent of the light intensity down to the lowest point we can prepare. So we were really surprised and were informed by other teams like Dajin's group and the Hanno group. They also observed similar zero results. So this just means the theory could miss something. That means the calculated spinning time on photoexcited rate are wrong by at least 2 orders of magnitude. So here's a summary of all known results of the measured steeping time. You can see only the first two experiments kind of agree with theory. All the others deviate from theory up to 5 orders magnitude. This means this full atom collisions in the short distance is just beyond modern quantum dynamics calculation. And there are multiple possible reasons, which I cannot dig into detail because time limitation. But I personally think in the future, it would be nice to build such a setup to directly detect the stacking complex of chemically stable molecules, just as contemplated in Harvard. But as experimentalists, we have to go on to find the effective solution. So here we use the effective solution of microshielding. So this nice solution was first proposed by Kais, Dolan, and their colleagues in 2018, but really working proposal, and first demonstrated in kerosene fluoride in tweezers. So thanks to the long-lived excited state of molecules, this microshielding really works in compared to the optical shielding of atoms. So basically, the macro coupled the attractive branch and the repulsive branch of those two molecules, intermolecular potential, and create all direction shielding Hall here. To make it work, in the experiment, we need circular polarization and strong field strength. So if we take a close look of the shielding picture, you'll find a classical analogy of like two compass needles in external Earth field. When they are far apart, they interact like two dipoles. But when they are close, they just realign themselves due to the strong dipole interaction. But in the classical picture, they minimize the energy. But in quantum world, depends on the quantum state, you either maximize or minimize energy. So here, the two molecules in the upper jet state, they find a way, they become always repel each other. So since the shielding works very well and reduce the collision loss of the two molecules, we can reduce this multiple channel collision into a single channel collision problem. So our theoretical collaborator Tosher found a really nice effective potential formula, which that you can decompose those intermolecular potential into a van der Waals shielding core, which scale with R to the 6th, plus anisotropic dipole interactions, which scale with R to the 3rd power. So these coefficients, like C6 and C3, can be really tuned by multiple knobs, like Rabi frequency, detuning, and ellipticity. So this gives rise a really flexible, tunable intermolecular potential. So here I just show you an example of how those tuning knobs can control the intermolecular potential. For example, when we increase the Rabi frequency, here is the intermolecular potential in the microwave field plane. In the far distance, it's attractive. But when the molecules are close, you see the shielding part. In between, you find the attractive potential. The attractive potential well depth increase as you increase the Rabi frequency. So this is important to give rise to new type of scattering resonance. I will talk about it later. So another tuning knob, as example, is the ellipticity. When you make the polarization more elliptical, it's not only break the rotational symmetry, but also increase the attractive potential well in the long axis of the polarization. So this really can control the intermolecular potential symmetry, shape, and strength, which I never see in atomic system. Another difference is that the large shielding core is much larger than the hard core of the atoms. This can give rise quantum manifold phenomenon beyond dilute gases. For example, when the shielding core is really comparable to the particle spacing, the condensate of macro-shielded bosonic molecules has a very low condensate fraction, just like helium-4. So this is and with this anisotropic tunable interactions, I really cannot imagine what we will find in this system in the future if we can manage to pull them down. All right. So in short, to make the working experiment, so we use a simple helical antenna. This was made by Andres, but in the experiment we found it's also important to put a metal foil in the right angle, which we never expected. But with these combinations, we managed to get a large radio frequency with good circular polarization. And this is just a result. This is the measured elastic collision rate coefficient and loss rate. As you can see, when the macro detuning is large, that means the macro shielding is not working yet. The measured loss rate is close to the universal two-body loss. This is as expected. But as you reduce the macro shielding detuning, increase the effective dipole moment. This also improves shoot, as Sebastian talked about. And this gives us a shooting factor of 10 and make the molecule sample has a lifetime of about half second. We were very excited about this result. But in the same time, the measured elastic collision rate can increase by more than 3 order of magnitude. This is because the elastic collision cross-section scale with the dipole momentum to the fourth power. So this gives rise quite a large good to bad collision ratio, like about 500 in experiment. It's so large that the cloud enters the hydrodynamic region. So this is another thing that in the future that we want to study, like the strongly hydrodynamic molecule cloud. So we are also very happy to see that recently, like in Sebastian's lab and Fabian's lab, the macro shielding also works for bosonic molecules. So with this good to bad collision ratio, it's straightforward to do the evaporation just by lower the trap depth gradually in time. So this just shows without evaporation, we thermalize molecules to about 1 Fermi temperature. But in the end, by lower the trap depth, we can get about 36% Fermi temperature, which you can see the momentum distribution of the molecules deviated from the orange Gaussian distribution and fit better with the Fermi-Dirac distribution. So this gives rise a few new possibilities. For example, observe the Fermi surface distortion and collapse and load them into a lattice to study spin models. So we have some intermediate results, but it's not conclusive. So for the moment, we focus on electroassociation tetramers, which I will show you very soon. But before that, I would point out a few challenges of this field. To get more degenerate gas. So for us, we want to reach below 10% Fermi temperature for fermionic molecules. But there are a few challenges. For example, these two are common problems when you pull down fermionic atomic gases. First, the elastic collisions are surprised when the Fermi gas are deeply degenerate. For example, 0 when you go to absolute 0. The second is the whole heating rate of Fermi gas also increase as you reach a lower TOTF and with shorter lifetime. And the third challenge is that the molecule creates so frequently, this cloud becomes hydrodynamic. The rethermalization rate just separates the trapping frequency as we measure here. And the last challenge, like Sebastian and Fabian observed in bosonic molecules, they observe additional loss, probably beyond two-body, in small detunings. So I'm really curious, Sebastian can correlate this to fueling bounce, which is very interesting. So I think we must solve those problems to really reach a much lower temperature to observe quantum many-body phenomena in the future. All right, I think I have a few minutes left, so I have to move on. Okay, so I have 5 minutes, right? So as I mentioned, when we increase the ellipticity of the macrofield, we can increase the attractive potential depth, which can host one bound state on second bound state. We call this fielding bound state, so which is first predicted by strong bond in OH molecules and growing in those vacuum molecules coupled with microwave. So when Andres was optimizing the shielding with a phase array antenna, he sees some weird resonance features. So we asked test, could this be scattering resonance? Test said yes. So yes. And we to observe those really precisely, we developed a simple antenna, which is so-called dual feed waveguide antenna, which you get to orthogonal quasi-linear polarized field. You can combine them to generate near circular polarization. And by tuning the relative phase between the two feeds, you can tune the polarization from linear to circular very easily. So with this antenna in hand, we just tune the polarization from near circular to linear, increase the attractive potential depth. Indeed, we observe when the circular polarization is good, we observe the loss very below the universal limit. But when the ellipticity is high, we see a resonance feature, which agree with Kai's calculation very well. And when we further increase the ellipticity, we can see the resonance move to the larger detuning, and the second resonance appear. This quantitatively shows the existence of the fielding resonance. Okay. And this resonance is not only useful to enhance the loss, but also to resonance tune the scattering length in the resonance channel in the py direction. So just give you a few insights. Here's a comparison between the fielding resonance and phasor resonance. So the most important difference is that those fielding bound states are really large, like 1,000 baryons. And compared to the fast-file resonance, which is close to the short distance, this makes the bound state lifetime really long, like 100 milliseconds. So, and also development of those fielding states are quite large. And very importantly, as long as the development is quite large, one can always find fielding resonance for those molecules. This is a calculation back problem. All right. So, with the observation of fielding resonance, we move to the creation of tetratomic molecules. So we start a degenerate Fermi gas of dynamics. Then we slowly ramp up the ellipticity of the microwave, increase the attractive potential depth, and populate those bound states. So here's the pathway to associate with tetratomic molecules. Here's the ellipticity and rapid frequency. To observe relatively long-lived tetramers, we have to increase rapid frequency. So for this purpose, Xin-Yu has spent a few months to create his 200-watt steam pump, which can increase the rapid frequency by 3 times. So, our first measurement is we just jump the ellipticity to a region where the bound state exists, but modulate the ellipticity. And when the modulation frequency resonant with the binding energy, we see a dip in the loss measurement. And the measured binding energy agree very well with the prediction of the binding energy. This really demonstrates the existence of the bound state. In the second measurement, we run over the resonance slowly, create those tetramers, and hold them. And we can see those decay time of this tetramer signal depends on the ellipticity on binding energy. So generally speaking, when the binding energy is higher, they decay faster. This is because the overlap between the bound state and the scattered state in the lower depth channel is larger. So in the end, we have maximally a lifetime of about 8 milliseconds near the collisional threshold, but we expect a larger lifetime if we increase the rapid frequency. Okay, and here is another evidence of existence of those created tetramer state, where we create the tetramer state, but we modulate this elliptic state and populate those, dissociate those tetramers into scattered state. Very interesting point is those modulated dissociated tetramer state shows those new move shape, which excited this p-wave angular symmetry, which reveal the angular distribution of the bound state in the moment of space. All right. So in the last point, I just show you so a few minutes how we determine the temperature of those tetramers. So here we use a peeling pulse, but high ellipticity, where those tetramers decay very fast. Now we take a difference between the images with tetramer and dimer, and with only dimers, we can deduce those temperature of those tetramers to be about 100 nanokelvin, and the phase space density about 4%. So here you can also see those conversion efficiency of those tetramers increase when you reduce temperature. So we expect higher conversion efficiency if we can further cool down those samples. So just give you a bit more insight, so you can see how the known polar molecules summarize. Those weakly bound molecules are 1,000 times colder than those deeply bound molecules, so which provide a good starting point to transfer them into a deeply bound state. So as an outlook, in the future, we want to further cool down those Fermi gas of dimers to reaching below like 10% Fermi temperature, where in principle we could observe those p-wave superfluid and maybe a crossover to the D6 tetramer. And second is, in principle, we can turn on the laser and look at the excited photo excitation spectrum, search for isolated excited state, and maybe transfer those deeply bound tetramers to deeply bound tetramers. If this works, one could imagine like a scalable assembly from dimer to tetramer onto octamer, or even more. So in summary, we have so the collision of molecules in short range is still mystery, but we managed to stabilize them with macro shielding and find a new type of field-link resonance and create a larger molecule. In the future, we want to cool down to observe this dipolar PCS easy crossover and maybe scalable assembly. So don't miss those two posters by Andres and Schreiber. So in the end, I will look at some of the team, especially Andres, Xin-Yu, Roman, and Michelle. So Roman's talk I think is on Thursday now, something, and also Emmanuel team. Okay, great. And especially theoretical collaborator Thijs, Foster, and Paul. All right, thank you.
Thank you very much. Okay, so we have some brief times for
Thanks for the great talk. What's the so a lot of the issues with heating that you talked about aren't unique to molecules; they also apply to atoms, a fair amount of atoms. So, can you comment on which aspects are unique to molecules?
Well, as I said, the intermolecular potential is highly tunable, and also it's long range. So I think this is absent in atomic Fermi gas. Also, the large shielding power is very different from atomic Fermi gas. So which makes the anti-bunching similar to a helium-3, helium-4 system.
So is the free body loss coefficient much larger for the molecules than for atoms?
No, I think we dominantly observe full body loss here. And in principle, by increase the rubbish frequency and improve the phase noise, one could suppress those full body loss. As long as you're away from those scattering resonance, I believe the free body is low as shown by Sebastian.
next question.
Yes, hi. A very quick question. Do you have any expectations about the elastic properties of the tetramers? Do you know anything about it, or?
Well, we have estimation because the dipole moment is twice of dimer, so the elastic collision rate is actually like 10 times faster. So that means within this 10 millisecond lifetime, they already played more than 20 times. But other than that, I think we have to maybe measure more.
Thank you. Another question? If not, maybe I will ask, because like you want to produce the ground state tetrameters, and we are looking at this, but the problem is that the size of your like field link state is huge compared to the short range states of the ground state.
Yeah, we have to see experiment. I think it's unknown.
Yeah.
But then this will be interesting.
Okay. Then thank you once more. And the next speaker is, please, thanks.